This lecture will explore various properties of solutions that we've defined in a previous lecture, solutions being solute and solvent combinations. So here are the key concepts that we'll be doing for this particular lecture. We'll look at factors that affect the rate of solution formation. So you can do certain things to affect how fast a solution will form. We'll also look at the concept of solubility, which is the amount of solute that will dissolve in solvent. And those first two often get confused, but are actually different. So there's how fast a solution can form, and then there's how much solute can go in a solution. Now, based on that, there's saturated versus unsaturated. A saturated solution it has reached its solubility max, and we'll be discussing that. The next little topic will be miscibility, and what miscibility is when you have two liquids coming together. So it's not necessarily a solute-solvent situation, it's just whether you can mix two different solutions. Finally, we'll be looking at the relationship between solubility and temperature, both for solid solutes in a liquid solvent, and then we'll also be looking at the solubility of a gas solvent, a gas solute, and how that changes with temperature. And then for gas solutes in a liquid solvent, we'll also be looking at the relationship between solubility and pressure. So higher pressure, how does that affect solubility? First, factors that affect rate. So this is how fast can you make a solution form. And there's an important point, and I tried to underscore this at first. This is about how fast the solution will form, not the amount. There is a certain maximum solute that you can put in a solution, and this is not going to change that number. You can just get to that max faster. So here are the three things that you can do, and I think a couple of them are kind of obvious. You can stir. So if you imagine, say, water, and you put some salt in there and you just dump it in there, it'll probably go down to the bottom and sit there for a while, and maybe if you came back at some point a couple hours later, it'd be all mixed up because the liquid molecules are moving around. But you can help that along by mixing it up and stirring it. What that does is that increases the frequency of solute-solvent interaction, and so it's going to make the solution form faster. Another thing is temperature. Higher temperature means particles are moving faster. Faster moving particles means they're going to mix faster, so you're going to have a faster rate of solution formation. And lastly, particle size or surface area. If you decrease the particle size, so if you make smaller chunks, or if you increase the surface area, you'll have a faster solution. And maybe an example that makes sense here is if you were to make hot chocolate, and you tried to make hot chocolate with like that powdered stuff that comes in the little packets. You put it in, you mix it up, it happens pretty fast. Whereas if you were to just take a big brick of chocolate and dump it in there, it might take a while before all that chocolate dissolves. It probably wouldn't be hot chocolate anymore at that point. So again, particle size. And I'm going to explain that on the next slide because it's a little more complicated. Now, the key point here, again, it's just rate, not amount. But what each of these three factors is really doing is it's increasing the frequency for solute and solvent interaction. So it's allowing those two to get to know each other faster. It speeds the process along, as opposed to it taking time and just relying on basic particle motion in the liquid. So we're going to look at two examples, one with less surface area, being a larger particle, and one with smaller particles, which would have more surface area. So here's your big particle. It's a big brick of whatever, and it has less surface area than this. And to prove that, and it's not maybe a perfect picture, but what I want you to see is that these over here are all like individual granules, where this is one big block. So, this big thing is made of a bunch of smaller cubes. So this would be like the cornerstone here. There's three faces that are available to the solvent. So if this is the solute particle, there's three faces here available. There's the one facing out, there's the bottom, and there's the side. Everything else is like inside this cube. Over here, this one, it's kind of right on the surface here, There's only one surface available. Everything else is obscured. So there's only that many places where the solvent can attack the solute and make an interaction. Whereas one of these separate particles that's all by itself, you have 6 faces that are available. So if you imagine this one particle down here has 6 faces available, this one, this, all of these have 6 faces available. But the corresponding ones over here, this one has 3, the one next to it would have, what, 2? This one has 1, so there's just less surface area available in the big one versus the small one. This is going to have a faster solution because there's all these places where the solvent can attack. Next, the concept of solubility. Now this is amount, so this is different from rate, but it is amount, how fast, or not, it's how much solvent, or how much solute can dissolve in solvent. So here's our formal definition. It's a specific amount of a substance that can dissolve in a solvent at a specific temperature. And this is maybe where some of the confusion comes in because temperature does affect solubility. So temperature does affect the rate like we just saw, but it also does affect the amount. And again, that's where some things can get a little confusing. So this is an example of solubility. At 20 degrees Celsius, the solubility of sugar is 203 grams per 100 grams of water. So in 100 grams of water, you can fit 203 grams of sugar. At the same 20 degrees, the solubility of salt is only 36 grams. So if you were to have 100 grams of water, you could only fit 36 grams of water in that. And after that, it would be what's called saturated. And we'll look at that a little bit later on. Now here's the temperature issue that we were just looking at. Here's a graph from the textbook. On the y-axis you have solubility, which is grams of solute per 100 grams of water. On the x-axis you've got temperature. And you got a bunch of different solutes. So the one we were just looking at was sodium chloride. It's kind of this orange color. This one's a little interesting because the solubility actually doesn't change over a wide range of temperatures. So you can pretty much fit that 36 number in no matter what. But if you look at, say, potassium nitrate, the purple here, it's got a pretty low solubility at the lower temperatures. And then as the temperature heats up of the solvent, of water, the solubility just takes off and goes huge to where you can get up to probably about 150 grams in at a higher temperature. The reason for that is because more energy available in the water, they're moving faster, more of that potassium nitrate will be able to be dissolved. There is one little exception here, not one, there's more than one, but this is the one that's shown. It's kind of an obscure little molecule, but this one, ytterbium sulfate, actually you get less solubility with sugar, or sorry, with higher temperatures. And this is just to show it's not a firm rule, but it's a general trend. Most of these have an increasing temperature and solubility relationship, but there are some exceptions. This one's negative, this one's flat.